Hey everyone, welcome back. So in this video, we shall take a look at some of the small miscellaneous models in time series, such as the random walk. So we'll first take a look at random walk with drift. So say WT is a white noise. So the model for random walk with a drift is given as this. So the time series at current point is delta plus its value at the previous time point plus the current white noise term. So again, because we have this xt minus 1 here, we have to worry about initial condition, right? So for t equal to 1, we need to set some value for x0. So we're going to set x0 to be 0. So that is the starting point for the time series. So the constant delta is called as the drift. And if delta is 0, then this model is just a random walk. If delta is not 0, it's random walk with the drift. Delta 0, then it's just a random walk. So let's see how this looks like, right? So I have a graph. The black graph is random walk with the drift. So delta is 0.2. And the blue one is random walk, is just a random walk. So delta is 0. So you can see that for random walk, it's basically deviating around this line at 0, and for random walk with the drift is drifting away from this flat line. So why is this called as a random walk, right? So again, we have delta 0, starting point is at 0, and say I generate white noise at the first time point, and its value is minus 0.61. So the value of my random walk at time 1 is just W1, so that's minus 0.169. At time point 2, I get this value for white noise. So the value for random walk at time 2 will be updated with this equation. So its value at time point 2 is now 0.678. Same thing for time point 3, we again generate another value for white noise, and now the value for x3, right, or random walk at time point 3 is updated to 1.1778. So there is another way we can look at this. So think of a particle and think of x0, right, is as the position of the particle at time 0. So the particle is at 0 at time 0. At time 1, the position of the particle is now updated to minus 1.69. So it takes a step towards the left, right? And the magnitude of this step is basically, or it takes a step to the left of size, the step size is 0.169. At time point 2 again, it takes step to the right now, right? It takes a step to the right and the step size is this 0.847. And so this is the final location of the particle at time 2. At time 3 again, the particle takes a step to the right again, right? And the step size is this, is given by W3. So to visualize this, at time point 0, this is the position of the particle. At time point 1, it takes a step to the left of size given by W1 or the magnitude of W1. At time point 2, it takes a step to the right. So the particle is moving either left or right, right? It's taking random or it's taking steps of random step sizes, right? And that is where this random walk comes, where the term random walk comes from. You can think of it as this particle taking a walk along the real line. So here's a quick exercise to make sure you get a hang of the equation and the model, right? So show that this random walk at point t, this xt, can be written in this way. Show that this equation holds true. So this result is useful for writing code. So if I were to ask you to write our code to generate random walk series, then this is a result that you would use, right? This would make it very easy for you to write your R code. So go ahead and take a shot at showing this and think about how you can use this result to generate a random walk. So here's another different concept of signal in noise. What do I mean by this? So there are many models in time series that assume that there is some basic underlying signal, right? Maybe it shows, the signal shows some periodic variation, but the signal is contaminated, right, by some noise. So for example, this is my model for time series, right? This is the signal, right? So this is a cost function. So you know that it's going to go up and down. It's going to have a periodic nature. And I've added this white noise to it. So you can think of it as this is the signal, right? And it's contaminated by this white noise. So you will see where the word, why I'm using the word contamination, right? So an image of, or a graphical display of this will make this clearer. So I'm going to generate time series, right, where this is a signal, and I'm going to vary this WT. So in the first, or in the topmost graph, right, you see this is the equation of the graph. There is no noise, right? It is just the signal. And this is how the graph looks like. There's smooth curves going up and down. There's no noise here. Now, if I add a little bit of noise, so I'm adding standard normal noise to this, you see how the graph now looks like, right? Now you have these squiggly lines, but you can still basically see the underlying periodic pattern. So these lines or these deviations here, right, the squiggliness or the roughness indicates that there is error in the data, right? It indicates the presence of a white noise, or indicates presence of noise. So what happens if I add more noise? So you see I'm adding a white noise which has this variance given of 25. So this is a lot of noise that I'm adding, and this is how the plot looks like. It just looks like basically like a flat line going up and down. So basically you cannot see the periodic nature of this signal, right? So the signal is basically overwhelmed by the noise, that the signal is lost. So if there's too much of noise in the data, the signal is lost. So it means that there's so much noise that you cannot see the underlying patterns in the data set. So that's all for this video. We shall see how to calculate the mean of time series data set in the next video. Bye.